Hello everyone. So before going for a long leave because of Corona lockdown, we had started histogram modeling in spatial domain image enhancement. I hope you all are doing well at home. You're staying at home and you are fighting for the Corona spread. So my advice is to stay safe and sound at home and fight for the Corona. Today we are going to discuss the topic histogram modeling. So there are three types of histogram modeling we can use in order to enhance the image. One is a histogram stretching and histogram equalization, and the last type is histogram matching or specification. So what is a histogram? Histogram is nothing but, suppose if you consider image which is made up of number of gray levels. Now, if you consider the number of gray levels, the one of if you select one of the gray level from the image, and if you see the number of occurrence for that particular gray level, if you consider here in this example, if this I represents a gray level and h of I are nothing but the number of pixels. The number of pixels are nothing but how many times the 2 is repeating in the image. That is, the gray level 2 is repeating 10 times in the image. So if I draw the graph for the number of pixel versus the gray level, that is the input gray level, I will input gray level also known as intensity gray level. I will be able to draw the number of repetition for the pixel value 2, how many times? 10 times. It provides me the histogram for the gray level 2. Similarly for gray level 1, 1 repeats 2 times or twice, 3, 0, 4, 0, 5, 0. Then the gray level 6 repeats 5 times, so it touches this 5 color line. Then 7, uh, 7 repeats 7 times. Then 8 repeats 3, 9 repeats 9 times, 10, 11, 12, 13, 14, 15 up to L minus 1 level, or the number of gray levels. You can actually plot a histogram for each and every gray level value. Now here in example we are considering the K, that is levels are 16 and 10 pixels have intensity value at a 10 pixels, and the number of 10 pixels are having a gray level value too. So this is just an example how we can actually plot a histogram for the specific gray value. Means it gives you the probability of occurrence for that particular value. So how many times the particular gray level is repeating for that particular image, which will give you the histogram plot, the entire histogram plot. Okay. So there are some interpretations about the histogram, how we can actually read the histogram. If you look at the first picture, in the first picture it is not cleared image. So because the picture has been illuminated poorly, or you can say it has a very limited histogram level. Means if you consider the values 0 up to 256, here in image processing we consider 0 से लेके 255, that is 0 से minus 0 से लेके L minus 1. Means if you consider, you are actually utilizing only the limited area or small area from 0 to L minus 1, means it will give you the low contrast image. That is why the image is not clear. In order to improve this image, I need to distribute all these histogram, I need to distribute all these pixel value from the range 0 to L minus 1 or 0 say to 55. So normal contrast, if you now, this image is better than your previous one, that is the first one, because it had something, it had some valuable information. Now it is not a poorly, or you can say mm, the histogram is in a perfect manner. You can say it has been spread it from this 0 level to L minus 1. Okay, then I can plot a histogram, means I can modify the histogram for the normal or low contrast in order to improve the image like this. Means the histogram is actually distributed uniformly from level 0 to 256. It acquires the 0 as well as 256. Means I have spreaded my histogram from minimum value to maximum value, which will give me the high contrast image of that input image. High contrast means you will have the maximum pixel values as you are covering from lowest 0 to L minus 1 value. So this is the basic difference between the low contrast, normal contrast and high contrast. Okay, so there are basically different types of interpretation you can actually make as you consider the contrast of an image. If you consider, if you have the maximum histogram will lie nearer to the 0, it will give you the dark image, because it will be very near to the 0, because in intensity axis we consider the 0 as a dark, that is a black, and L minus 1, that is the final value, will be a bright or brightest, that is white. So 0 represents black, L minus 1 represents a white. If you have maximum histogram nearer to the 0, it will be the dark image. Okay, and if you have a very this histogram is situated at L minus 1, then it will be the light image. And if you have if you are covering very limited range from 0 to L minus 1, then it will be the low contrast image. And high contrast means you are covering from 0 to L minus 1, 0 to L minus 1. Uniformly distributed histogram, uniformly distributed your gray levels, okay, with a pixel value. So dark image will contain the maximum histogram nearer to the 0, light image nearer to L minus 1, and low contrast means you have a gray level pixel values are they are actually covering very small area from the entire range. And if you cover the maximum range or the entire area of 0 to L minus 1, then it will be considered as a histogram of a high contrast image. And this is the output. If you see, the very clear image will be the high contrast image. This is a low contrast image, very dark shade you can find, light image and dark image. Now this histogram shows the histogram of this color image. When we consider a color image, we need to consider the histogram for a red color, green color and blue color. Okay, so this is nothing but a red color histogram. From the red means you are considering each and every pixel value. Now what is the RGB? RGB color image is made up of 24 bits, which has 8 bits of red, 8 bits of green, 8 bits of blue. And if you consider the another type, that is the luminance. So luminance is the amount of energy that the human eye can perceive, or it is nothing but a gray level. Okay, the intensity, the amount of energy that you can absorb. Okay, so you have a red color histogram, green. When you combine all three, you will be able to create the color image. And this is normally it is covering the range from 0 to L minus 1. Okay, when you consider a gray level image, what is the gray level image? Gray level image is of 8 bit, so it has 2 as to 8, total 256 levels. L will be 256, L minus 1 will be 255. Okay, and the histogram shows the frequency of each gray level. Histogram means the number of gray levels, how many times the number of gray levels are repeating in the image. Okay, this is an example of gray level image. Huh. Now, if we consider a image, this is the image. Now I'm considering 3 bits per pixel image. When you consider 3 bits per pixel image means it has total levels 8 because 2 raised to 3. As it is 3 bits per pixel, 2 raised to 3 that is 8. L will be 8, L minus 1 will be 7. But the size of my image is 1, 2, 3, 4, 5, 6, 7. 7 by 7. So 7 by 7. M is equal to 7, N is equal to 7. M into N will be 49. 7 by 7. So total number of pixels will be 49. You need to consider the maximum size or the maximum pixels in the image also. Okay, so these are nothing but the gray levels: 0, 1, 2, 3, 4, 5, 6, 7. As my image does not contain beyond 7, I can actually consider the image is a 3 bits per pixel. When you hit 8 means you are now in a 4 bits per pixel image. So 2 raised to 4 is what? 2 raised to you have to multiply 2 4 times, so it will be 8 2s are 16. 16, the value will be L will be 16, 15 will be the L minus 1. Now as the highest value is 7, I can actually accommodate this 7 in 3 bits of pixel. Okay, so the gray level, now from the image you need to write a gray level RK out of, and then 0 1 2 3 4 5 6 7, and the number of pixels, the number of pixels. अगर 0 है तो कितने बार कितने pixels are inside the image, you have to consider. This is the wrong one actually. Wait a second, we'll modify this. Okay, so I'm considering 2 as a 7, 2 as a 5. If I'm considering 2 as a 5, okay, and 0 repeats twice. So if I want to eliminate 2 twice, and I will replace the 2 by 0. Okay, now is it correct? Yes. Okay. Now the image is proper. Your 0 has 2 pixel, 1 and 2. 1 has 6 pixel, 1, 2, 3, 4, 5 and 6. 2 has 5, 1, 2, 3, 4, 5, and 3 repeats 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4 repeats 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 repeats 7 times. The number of pixels for gray level 5 are 7. So 5. 1, 2, 3, 4, 5, 6, 7. 6 repeats 6 times. 1, 2, 3, 4, 5, 6, and 7. The gray value 7 has 4 number of pixels. तो 7 कितने बार 4 टाइम्स चाहिए? 1, 2, 3 and 4. So the picture or the image is correct now. Okay, so I will actually draw a table which will contain the gray level RK and the number of pixel for that gray level. Okay. So 0 repeats twice, 1 repeats 6 times, 2 the number of pixel for the 2 are 5 times, the number of pixel for gray level 3 10 times, 4 9 times, 5 7 times, 6 6 times, 7 4 times, and from this I can draw the histogram. Okay, 0 repeats twice, 1 6 and this. Now this histogram is not a normalized histogram. Why? Now suppose in your image the value 3 repeats 100 times, so it will be very much complex process in order to draw the if the 3 repeats 1000 times, it will be very complicated process because you cannot plot a graph for 1000 times, or if the gray level value has 1000 pixel 1 lakh pixel 1 crore pixel in the image, you need to normalize. Now how to normalize means you need to divide the number of pixel for that gray level by total number of pixel of an image. Means if you have m into n size of an image, m is 7, like 7 by 7. This this image is 7 by 7, so 7 by 7 will be 49. 49 will be total number of pixel from the image, and then you will take the number of pixel and you need to divide by 49, so it will get normalized. So what is the advantage to normalize this? I will show you. Now to normalize you need to divide the total number of pixel with the number of pixel. If you consider 0 pixel, you will now 0 repeats twice, so 2 divided by 49 will be 0.040. 1 repeats 6 times, 1 repeats 6 times, so 6 divided by 49 will be 0.122. 2 repeats 7 times, so 7 divided by 49 will be 0.142. 4 repeats 9 times, 5 repeats 7, 6 repeats 6 times, 7 repeats 4 times, so total. Now if you see the value after normalization, it will not go beyond 1, because you are dividing the total number of pixels. You are dividing the number of pixel with the total number of pixels. You cannot go beyond 1, and it will be very much easy if I draw for this y-axis up to 1. Now in this example, none of the pixel has been actually crossed over 0.25. Now I can easily plot for the value 1 here up to this. I can easily plot because I am normalizing my gray levels. That is the advantage. And this will give me the probability of occurrence for that particular gray level. So 1, the probability of occurrence of gray level 1 in the image is 0.122. If I consider 3, the probability of occurrence, that is the probability of occurrence of gray level 3 is 0.204. This is nothing but the normalized version or normalized histogram. When you divide your number of pixel with a total number of pixel. Okay, this is normalized version. Now the different images can have a same histogram. Yes. In one of the university examination, that is Mumbai University examination of IPMV subject, it had been asked, can different images have same histogram? The answer is yes. How? If you consider these three images, half of the part contains white and half of the part contain another type of pixel, white pixel and gray pixel. If you consider gray pixel has a certain value and white pixel has a certain value, if you consider L minus 1 as a white pixel, and in the gray level in between L minus 1 and 0 has something, then half of the part or half of the area is covered by white and this. If you consider this, the half of the area is covered by the white and half of the area by gray. Similarly, half of the part is covered by gray and half of the part by this. So the different images can have same histogram. Now, if you plot a histogram for this, for the gray level, the pixel value will be half. If there are 50 number of pixels inside the image, 25 for the gray, 25 for the white, 25 for the white, 25 for the gray, 25 for the gray, 25 for the white. So different images can have a same histogram. Okay. Can we reconstruct the image from the histogram? No. The answer is no. Because you don't know now you can construct the digital image, but you cannot construct the image. That is optical image. Okay. You need to actually consider different types of technique in order to reconstruct the image, like image restoration technique. Okay. Because you need to consider the Fourier transform. The Fourier, you need to deal with the Fourier transform. You need to consider all these Fourier domain, the frequency domain techniques in order to reconstruct the image. Okay. Now the first type is histogram stretching. The basic simple formula for this histogram stretching is S, that is modified the sorry S modified image S can be represented by a transformation on input image R. S, that is output image, R is the input image, and T is the transformation. Now, what is the transformation? This transformation is nothing but S max minus S minimum divided by R max minus R minimum. That is S max S minimum जो desired output है, that is S, that is along your y axis, and this is R max R minimum, or you can say the modified output input ये input है, and then R, that is input R at present जो situation में जो भी R रहेगा, that is the input value रहेगा, you have to subtract the R minimum from the original value input image and you have to add S minimum. Okay. Now, why do we require the histogram stretching? If we have the histogram which is situated from this region to this region, it is not covering the entire range, that is 0 से लेके 255, that is 0 to L minus 1. It is starting from 84 and it ends at 153. It does not start from 0 and end at 255. Whenever I want to start from the minimum range and I need to end the same pixel value at L minus 1, I need to stretch. I need to stretch this end to this and this end to this. And I need to distribute the pixel value in between 0 and L minus 1. At that time means what? I am increasing the dynamic range. I can visualize my image for the minimum value as well as for the highest L minus 1 value. Means I am extending the dynamic range for the input image. For example, suppose you have the number of pixel and the input gray levels 0, 1, 2, 3, 4, 5, 6, 7. Okay. 0 repeats 0 time, 1 repeats 0 time, 2 repeats 20 times, 3 repeats 10 times the number of pixels for 4 30s, then a number of pixels for 5 40, then 6 repeats 0, 7 repeats 0. If I plot a histogram for this, my histogram will look like this. Okay, means it starts from 2, ends at 5. It is not covering 0 and 7, that is L minus 1. Okay. Now, from the diagram or from this table, I can actually have the different level of S and R. So S max, that is a 7 that I want to cover L minus 1. Hmm. If it is 3 bits per pixel, 2 raised to 3, 8, 8, L minus 1 will be. So S max is always L minus 1. S minimum is always 0. Okay, 0 and L minus 1. So S minimum, that is the desired minimum value, should be 0 and desired maximum value should be 7 L minus 1. R max, that is R max, that is input is at 5 and R minimum is 2, then 5 2. So I have S max, S minimum, R max and R minimum, R minimum, S minimum. I have R also. So first, when R when r is equal to 2, when r is equal to 2, I need to calculate the s. So by keeping r is equal to 2, s max 7 minus s minimum 0, r max 5, r minimum 2. So 7 by 3, okay, 7 minus 0, 5 minus 2, that is 7 by 3, that is 2.33 something, multiplied by when r is equal to first gray level, that is 2, for gray level value 2, minus r minimum is 2, 2 minus 2 is 0, 0 multiply by 0 will be 0, plus s minimum is 0, 0 plus 0 will be 0. So when r is equal to s is equal to 0. Hmm. Then when r is equal to 3, then again 3 here, you will replace the r value 3. You have s max, s minimum, r max, r minimum, r minimum, s minimum. You will calculate the value s. When r is equal to 3, s is 2.33, that is approximately 2. The approx value for the 2.33 is 2. After rounding down, the value is 2. 4. Similarly, 4.66, rounding up, we rounding up when you hit 0 0.5 and above. So 5, for 5, 6.9, and that is a 7. So you have covered from 0 से लेके L minus 1 7. When you were having 2 to 5, that is R minimum 2 and R max is 5. Now you have the new value, that is S minimum 0 and S max 7. Means you have stretched from 0 to 7. What will be the output? Now you have a new value. Now 0 repeats 20 because 2 has 20. 2 has a 20. Now you have a new input gray level, that is 0. Now 2 will be represented at 0 now in the output because you have stretched. So जब यहाँ पे था, now I am starting from new gray level value, that is 0 repeats 20 times because 2 का value इधर 20 है, तो ये 2 का value 0 को लग जाएगा, 3 का value यहाँ पे 10 है, ये 2 को लग जाएगा, 4 का value यहाँ पे 30 है, it will be considered for 5 level, and for the 5, the 40 number of pixels are repeating, so it will be considered for the 7. So I will redraw the graph like this. Okay. So that will be HK, the number of pixel for that particular output gray level, the output gray that is stretched. So before stretching the histogram, my histogram was very limited, or you can say this is nothing but a power distribution function or power density function. The range was very limited from 2 to 5. After stretching, it has been covering from 0 to 7. I have increased the dynamic range of a histogram. So this is histogram stretching. Now the next type is histogram equalization. Now in histogram equalization, similar, if you want to increase the dynamic range, either you can go for histogram stretching. It is very easy method to actually stretch the histogram or to extend the dynamic range. But one more type that you can actually, this is the most powerful type if you want to distribute the histogram of the input image equally around or all over through the dynamic range, that is 0 से लेके L minus 1. Okay, so this is a histogram. This is PR of R. Now the intensity levels in the image may be viewed as random variables in the interval 0 and L minus 1. Okay, intensity levels are from 0 to L minus 1. These are nothing but the gray level. Let P suffix R of R and P suffix S of S denotes probability density function, that is PDF. Probability density function. So the entire range will be considered as which start from 0 to L minus 1. Or it is, if it is not 0 or L minus 1, you need to make to 0 to L minus 1 or whatever after equalization. When you distribute equally the histogram or gray levels or number of pixel all over the area. Now you're considering the A image arbitrary PDF. that is this. The actual histogram you will find like this, like it does not contain the uniform shape. It is increasing, downgrading, increasing, decreasing, increasing, decreasing. Okay, this is nothing but the uniform, you can say uniform. So actual our desired output should be the uniform one, but you will not get exactly the uniform output after processing or after doing the histogram equalization on uneven part of your histogram. But the aim is to make it as nearer to the uniform. Okay. And now if you consider the value for this at s, it is nothing but the slope 1 upon L minus 1. What is the slope formula? Y2 minus y1 upon x2 minus x1. You have x2, x1, x2 and x0. Suppose if you have x2 minus x1, x1 is 0, x2 is L minus 1, y2 is 1. Suppose this is 1 and this is 0. 1 minus 0 divided by L minus 1 minus 0 will be 1 upon L minus 1. That will be the slope L minus 1 for the uniform, you can say, or for the one value. When the output value is 1, here L minus 1 will be the maximum input value. Mm. Now this should be the effect of histogram equalization. The result of applying transformation in this to all intensity levels are the resulting intensity S, that is output intensity S, have the uniform PDF independently of the form of PDF of R's. Okay, so the aim is to make the histogram uniformly distributed over the range of 0 to L minus 1. That is probability density function. That is the area. That is the density of histogram. This is also the density of a histogram. That is the area that you cover. Now in histogram equalization, you have two types or the multiple types of functions. Like suppose you have this and this. This is strictly one single value. If you are giving single value, you are getting single at the output. If you are giving single value at the input, you are getting single. But in many function, you are giving multiple times the input value, multiple values at the input, but you are getting only single value at the output. Okay, so it has monotonically increasing function showing how multiple values can map to a single value. This is, it is increasing, 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 then stable for multiple value, because it is stable for the one value, that is single value sq. Again it is increasing, 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 increasing. So monotonically increasing, as well as it has some stable value. That is a plot. You may have only the strictly monotonically increasing. Strictly means if you're giving anything in the input, it will have the different value at the output. For particular gray level, it will have a different output level. For particular gray level, it will have the different output level. That is known as strictly monotonically. It is not strictly monotonically. It is monotonically for up to this extent. Then it will give the single value for this multiple value, and then it is going again for the monotonically increasing. Now if you consider the output image S is nothing but the transformation on R, which has the value, that is gray level value 0 to L minus 1, 0 to L minus 1. Now A, the transformation R is strictly monotonically increasing function in an interval gray level 0 to L minus 1. Yes, when 0 and transformation R is also 0 to L minus